Alright, let's not delay anything. So what is ANOVA? Alright, so ANOVA is another comparison test, kind of like a t-test. But the thing about ANOVA is that you compare more than two groups at once. Right, so with a t-test it's only two groups, whereas with ANOVA you can compare 3, 4, and you can compare more than two groups. Right? And so how does ANOVA work? It compares variability within the groups and between the groups, right? So with the t-test, what we were doing is we were looking at the means of the groups and seeing if the difference between the means was statistically significant, right? So this would be the mean for this group, this is the mean for this group. With the t-test, we were comparing the means of the different groups. Now with ANOVA, what we're saying is that this group and this group, in this group the patients are different from each other, right? And in this group, the patients are also different from each other, right? But you can also see that there is a difference between this group and this group, okay? So if there is a difference between this group and this group, and the difference between the groups is bigger than the difference between the patients inside each of the groups, then we can say that the difference between the groups is because of something that isn't a result of patient factors, right? So what determines, so what do we mean by variability again? So within group variability, we have individual differences, right? So this can be an individual's height, this can be their weight, this can be their blood pressure, and so on and so forth, okay? And we have errors of measurement, which is basically that our measurements aren't always going to be 100% accurate, and so those errors also produce some variability. Now, between group variability, you'll also have individual differences, okay? So the patients inside this group are different from the patients inside this group, right? And that difference isn't just because of the drug, okay? And we also have errors of measurement between the groups, okay? So it's the exact same thing as over here. But with between group variability, we also have the effects of the treatment, right? So let's say this is our control, and this is our experimental group, okay? So other than the fact that these patients are different from each other and different from these patients, we also didn't give these patients the drug that we gave to these ones, right? And so if that produces a difference, which we can detect with ANOVA, if that produces a difference between the variability of the patients between the groups, then we can say that it's statistically significant. Right now, all of that was a lot of words. Let's take an example, but just as a final recap, within group variability, okay, will always exist regardless of whether the null hypothesis is true or not, right? So whether or not your drug works, there's always going to be, your patients are always going to be different from each other, and you'll always have errors of measurement. Between group variability is affected, okay? Because with between group variability, other than patient factors and errors of measurement, you also have the fact that you're giving the patients a drug. So here's an example, right? We have 3 different groups, okay? And their sample size is 9, okay? And so the first thing we want to do, and just to highlight, we have the mean for each group and a variance of 10 for each, okay? So our first step is to find the grand mean. Okay, now this might be given to us in the actual question, this might not be, but just in case it isn't, you find the grand mean by basically adding up all 30 of these values and then dividing them by 30. Okay? And that gives us a grand mean of 5.67. And so now that we have the grand mean, we can find the sampling variance. All right, which helps us calculate the between group variance. And so what you're going to do is you're going to take each one of these group means, and you're going to do group mean, okay, minus grand mean, and then you're going to take that difference and square it. Okay, and then once you add up the difference between the group mean and the grand mean for each of the three groups, you're going to divide that by k minus 1, which is the number of groups that we have. So that's k here. The number of groups that we have minus 1. Right, so I'm just going to try and demonstrate that. Just a second. So let's calculate our sampling variance for this example. Okay, so just to recap, our sampling variance is our group mean minus our grand mean, and then we're going to square the result of that. Okay, and then once we have the square of the result, we're going to add up this difference squared for each of the three groups, and then we're going to divide it by k minus 1. So for the first, so what that looks like is we're going to do 8.33 minus 5.67. That's our grand mean. So our first group mean minus the grand mean, and then the result of that is, let me just get out a calculator. So 8.33, 5.67, it's 2.66. And then we're going to square 2.6. So we're going to take that answer and we're going to square it, which gives us 7.07. And then we do that again for the next group mean, so that's 3.33. So 3.33 minus 5.67 gives you minus 2.34. And once you square that, hold on. So once you square minus 2.34, you get 5.47. And then for the final mean, we're going to have 5.33 minus 5.67. So once again, on the calculator, 5.33 minus 5.67. That's equal to minus 0.34. And once you square this, it'll give you 0.1116. Okay? So let me just clean this up a little so we have a bit more space. Alright, so now that we have the squared difference between each of the group means and the grand mean, we're going to add those up. Okay, so that's what we've done here. And then once we add them up, we're going to divide the result by k minus 1. So that's the number of groups minus 1. Okay, so what that's going to look like is you're going to do 7.07 plus 5.47 plus 0.116, and so that's going to look like 12.66, and then we're going to divide that by 3 minus 1, or divide it by 2. So divided by 2, and that's going to give us a sampling variance of 6.32. Okay? 6.328. Or 6.33. Okay? So, now that we have our sampling variance, what we're then going to do is we're going to calculate the between group variability. And that's the sampling variance that we got over here times the sample size of each of our groups. So that's going to be 9, which is our sample size. We have 9 participants in each group, times our sampling variance, 6.33, and that's going to give you 57. Okay? And then the next step is to find the average of the group variance. So that's going to be our within group variance. Okay, and so what we're going to do is we're going to find the average of the variances within the groups. So that's these numbers over here. So 10 plus 10 plus 10, right? Divided by 3, because we're trying to find the mean variance from within the groups. So that's going to be 10, okay? And then the final result to calculate our ANOVA value, or F, is we're going to take our between group variance, which was 57, and we're going to divide it by our within group variance, which is 10. Okay? And so that's 57 divided by 10, and the result's going to be 5.7. Now, since 5.7 is relatively large for an ANOVA, then that means that, or another way of looking at it is, since our between group variance is much bigger than our within group variance, then that means that the difference between these groups is more than the difference of the patients that are within each of the groups. Okay, so that means that there's something happening between the groups that's creating a bigger difference than the patients themselves are, or than patient factors are. Okay, so basically the drug works here, right? And so we reject the null. Now with the second example over here, once again, our first step is to calculate the grand mean between these groups. And so the grand mean here is 5.33. And then our number of groups, which is k, that's going to be 3 again. We have 3 groups. And our sample size for each of the groups is 9. Okay, so our first step is going to be to calculate the sampling variation. And again, that's going to be group mean minus grand mean. Then you're going to square the difference, add that up for each group, and then divide by k minus 1. Okay? So, for our first group, that's going to be 6.33 minus 5.33. So that's just going to be 1. And then 4.33 minus 5.33. That's going to be minus 1. Oh yeah, so 1 and then 1 squared is just 1. And minus 1 squared is also 1. So far, and then and then for our last group we have 5.33 minus 5.33, which is just 0. Okay? And obviously 0 squared is also 0. So then we're going to add these three numbers up. So that's 1 plus 1 plus 0. And then we're going to divide that total by k minus 1. So we're going to divide that total by the number of groups minus 1, or 3 minus 1. Okay. So that's going to be 1 plus 1 plus 0, that's 2, and then 3 minus 1 is 2. And so 2 divided by 2 is just 1, and so our sampling variance is 1. Okay? And so again, to find our within group variance, we take the sampling variance, which we calculated over here, and that's 1, and we multiply that by the sample size for each of the groups, which is 9 in this case. And so 9 times 1, that's just 9. As for our, our between group variance is our sample size for each of the three groups. So that's 9. So there's 9 patients in group 1, 9 in group 2, 9 in group 3. Then we multiply that by the sampling variance. Okay? And so 9, which is our sample size, times the sampling variance 1, that's going to be 9. And then our within group variance, again, is we take the average of each of the variances for each group, and then we find the average of those. So that's going to be 10 plus 10 plus 10 divided by 3, which is equal to 10. And then we take our between group variance divided by our our within group variance to get our ANOVA value, which is f. And that's going to be 0.9 in this case. And since that's relatively small, or because the between group variance isn't larger and isn't larger than the within group variance, then we say that the null hypothesis is true, but in this case the drug doesn't work. Right, so when do you say that the null hypothesis is rejected and the drug works? When the between group variance is significantly bigger than the within group variance. Now I'm not actually sure what how much bigger it has to be, but to stay on the safe side, if the f value, which is over here, is close to 1, then you generally just are going to reject. Then you're going to accept the null hypothesis and say the drug works. If it's much bigger than 1, then you're going to say that the null is rejected and that the treatment for this case works. Right? And so there are some assumptions with ANOVA. Right? And the first one is random samples and random assignment. So these patients were selected randomly, and we randomly put them in one of the three groups. The second one is normal distribution again. And the final one is that the variances are equal. Okay? Now, alternatively, if the variances aren't equal, what you can do is you can use a Welch's ANOVA, right, which is a little bit more complicated, and we don't actually have to know the maths for it, but if he does ask us questions, it's going to be about analyzing the Jamovi output for Welch's ANOVA. Right, so let's just take a look at that. So here we have the data for our 4 different groups, and then we did the analysis. And then we did the analysis for the groups. Now over here, our degrees of freedom, this degrees of freedom, that's going to be k minus 1, which we found, so k minus 1, that's this number. So it's the number of groups that we have, minus 1. Since we have 4 groups, our k minus 1 is 3. And then this degrees of freedom, which is for our patients, that's going to be the number of patients in the samples. That's going to be the number of patients across all groups minus the number of groups. Right? If that was a little bit confusing, then it probably won't come. So, like, you might want to listen back to that again, just to make sure you fully grasped it. But it's relatively low yield. Okay, so what we probably will get asked about is finding whether or not the result was significant, and finding out and understanding the effect size, right? And so if we have a normal ANOVA, okay, the way we get our F is by taking these two values, which is your two mean squares here, and then we're going to divide them by each other. And that's basically the same as what we did over here when we took our between group variance and divided it by our within group variance. Right, so this here would be our between group variance. So 216 is our between group variance, and our within group variance is 10.8. And so you divide 2.16 by 10.8 to get our F, which is 19.8 in this case, and that's very statistically significant. And finally, our effect size, which is eta squared. So we're going to find that. So we're going to find that by taking the sum of squares. We're going to take the sum of squares from this residuals area, and then we're going to divide it by the sum of squares from the treatment row. Okay. So that's going to be 648. Wait, no, that's backwards. So that's going to be 391.4 divided by 648.1. Okay? And that gives us an eta squared of 0.6, or an effect size of 0.6. Now, if we're given a one-way ANOVA, or a Welch's ANOVA, you'll notice that our degrees of freedom 1, that's just k plus 1 again. That's k minus 1, sorry. It's the exact same as this one. Degrees of freedom 2, you can just ignore that. I still don't understand what that is, after having read about it for 3 hours. And then our F, which we calculated over here, is 18.8. Now you'll notice it's a little bit lower than this ANOVA score because we're assuming that the variances are different, and so it basically makes it a little bit more careful, and it lowers the F slightly. And the final result is definitely statistically significant. So again, effect size, right? You can estimate effect size using eta squared. Okay. So that was the between group sum of squares divided by the within group. Is that right? Divided by the total sum of squares. Okay. And so that's going to give us an effect size of 0.62. Alright, so just to recap, our eta squared, which is our effect size, is you're taking the sum of squares for the residuals and you're dividing it by the total sum of squares. okay, which is going to be 0.62. And if you want significance, you look at F and you look at P. Okay? And so when you want to report it, you can basically say that this is very significant, that the ANOVA for this test was highly statistically significant, and it has an effect size of 0.62. Okay? And then the next thing that we're going to talk about is post hoc tests. Now, post hoc basically means afterwards, so it's an after test, right? And so once we've proven that a result is statistically significant, we need to know that which one of the groups was different from the others, right? So if we look back at this example over here, we had a no therapy control and a placebo. We had a no therapy control and a placebo, as well as 2 therapies that we tested, right? Now the thing is that when we calculated our F, we proved that there was a difference between the groups, okay? But what we didn't manage to prove is which group was the one that was different. And so what we're going to do with the post hoc test is we're going to identify which one of the groups is the one that's different, or basically which one of the treatments was the better one. Okay. Now another reason why we might do this is the other reason why you might do this is if you make your hypothesis after you've already collected the data. Okay? So let's say that you've already proven that there is a difference between the groups, and now your new hypothesis is that the new age therapy is better than the conventional therapy, right? Rather than collecting a new sample and running the test all over again, you can just perform a post hoc test on the groups. Now the final reason why you might want a post hoc test, a third reason why you might want a post hoc test is if you're p-hacking, right? Which sounds a lot cooler than it is. Basically, you're running a bunch of tests one after the other to try and get one that turns up to be statistically significant, right? So you can run to your boss and shout, "Yo, I had a positive result, the drug works," even though it doesn't, right? And remember, because we're working with a p-value or an alpha of 5%, there is a 5% chance that this happens anyways. And so if you're p-hacking, what's basically happening is you're shooting for that 5%, right? You're rolling the dice over and over again until you get a result that you like. The final reason why we do post hoc test is to lower family-wise errors, right? And basically, if you look here, you'll notice that the p-value is very high. But the issue is that the more groups that we have, okay, the more groups that we have, so the problem is with doing more than one test at once, which is we're comparing no therapy to placebo, no therapy to conventional therapy, and no therapy to new age, and then placebo to no therapy, placebo to conventional, placebo to new age, and then conventional to both. Conventional therapy to no therapy, conventional therapy to placebo, conventional therapy to new age, and then new age to all 4 of them. The problem with that is that it introduces more errors that basically increase the chance that you'll reject the null hypothesis even though it's false. Okay? And so this is still statistically significant and you can accept it, but you can't quite yet say which one of these is the drug that works. And so you have to run post hoc tests to identify that. And you have to run these post hoc tests because if you try to just look at the data and basically eyeball it, what you're going to end up with is a much higher alpha, or a much higher chance that you accept the null hypothesis. Okay? So that's our family-wise error again. We're comparing many groups together. So our alpha, or the chance that we reject the null hypothesis, even though it's true, is going to increase. Okay, so you don't have to worry too much about y. It's just that as we increase the groups, the alpha increases. So the first way that we can do it is we can do a Bonferroni test, right, which is the simplest post hoc procedure. And basically what you do is you take your alpha, you take your old alpha, and you divide it by the number of tests that you've run. Right, now if you remember over here, we had 4 groups. We had no therapy to placebo, no therapy to conventional, and no therapy to new age. We had placebo to no therapy, placebo to conventional, and placebo to new age. We had conventional to no therapy, conventional to placebo, and conventional to new age, and then new age to no therapy, new age to placebo. So if you add up the number of lines that I've drawn over here, so that's 1, 2, 3, 4, 5, 6, we've run 6 tests, right? We've made 6 comparisons between the 4 groups. Alright, so what our Bonferroni corrected alpha is going to be our old alpha divided by the number of tests, which in this case is 6. And we'll look at this later in a data set or in a table to sort of help demonstrate that. You also have Fisher's LSD, which you can actually do before you've collected the data. Right? But if you're going to do it as a post hoc test, you can only have 3 group means. And this one has the highest power. Right? So it has the highest ability to reject the null hypothesis when the null hypothesis is false. Okay? And finally we have Tukey's, which is what you can use whenever you have more than 3 conditions. Right? It's the most powerful test after Fisher's if you have more than 3 conditions, if you have more than 3 means that you're comparing. And it's also very powerful. Now, if you have more than 6, you're probably going to want to use a Benjamini-Hochberg test. This was only mentioned once throughout the whole PowerPoint, and so there wasn't really any information given about it. But as a general rule of thumb, Tukey's always works. Fisher's is better if you have 3 means, and Bonferroni is the simplest one. Okay, and so here we have the data in Jamovia. As you can see, there are 6 comparisons that we're making. No treatment to placebo, no treatment to conventional, no treatment to new age, placebo to no treatment, which is this one, placebo to conventional, placebo to new age, and then conventional to no treatment, which is over here, conventional to placebo over here, and conventional to new age. And then new age to all 3 of them. To all 3 of no treatment, placebo, and conventional. Right? So, when we're looking at the table, right, we start with our p-value, okay, which we more or less calculated by just running a t-test. We ran a t-test between no treatment and placebo, no treatment, and then we ran another t-test between no treatment and conventional, and then another t-test for no treatment and new age. And we had p-values for each of these 6 tests. Okay, and that was our Fisher's LST p-value, right? Jamovia doesn't actually doesn't actually write Fisher's for this one. It just says p-value. And then we corrected that p-value once using Tukey and once using Bonferroni. Okay, so again, with Bonferroni, you just take whatever this p-value is, and then you divide it by the number of tests that you've done. Sorry, you take whatever your original alpha was, your original p-value, and you just divide it by the number of tests that you've done. Again, you don't really need to know how to understand most of this. All you need to know is that this one's Fisher's, this one's Tukey's, this one's Bonferroni. and that's it. And then this is a second example over here, just looking at Chuukis. And you have your p-value between each of the four groups. Okay, so the p-value is over here for a Chuukis test. Again, Chuuki is the one that we use for more than 3. If you have more than 6, then you can switch to a Benjamini-Hochberg. And yeah, that's it. Bye.